Okay, we're going to talk about how you actually write the solution if you have a linear system of differential equations with complex eigenvalues, which, as I said in the previous video, it's not an easy process to write the whole solution. So you may have to do it on a homework problem. I think that's okay. We've got a formula for it, as you see right here. As a test question, I don't know, maybe, but probably unlikely you would see that as a test question. More common would be to just determine if it's a stable spiral or an unstable spiral or a neutral spiral. Okay, but nevertheless, here's how we're going to write the solution. So our eigenvalues will be complex conjugates. Okay, one of them would be alpha plus beta I, alpha minus beta I. And okay, we're going to think of our eigenvectors will also be complex conjugates. And those would usually have I in it as well. Okay, we actually don't end up needing to use both vectors, as you'll see why. We really just need to know the real part of the eigenvector and the imaginary part of the eigenvector, which I'm calling V and W. Okay, so the solution looks like this. This is from the book. There's not a great explanation for it. So let's not concern ourselves with that right now. If you're curious, you should probably do some research on this and convince yourself how this formula comes about. But it exists, so we might as well use it. Okay, so x bar of t will be c1 e to the alpha t. That's the real part. We saw that when we were talking about on the previous video. And then you can see this is Euler's formula being utilized here, times v, I'll talk about that in a second, why that's a vector, times cosine of beta t minus w, same thing, times the sine of beta t. And then we have a second part of this, c2 e to the alpha t, vector v times sine of beta t, plus vector w cosine of beta t. So let's work one example here. Here's my system. The matrix associated with that would be 1, -5, 1, -3. Okay, I'm going to find my eigenvalues. The determinant of a minus lambda I set equal to 0 gives me the quadratic lambda squared plus 2 lambda plus 2 equals 0. I need the quadratic formula, so I'll have negative b plus or minus b squared, square root of b squared minus 4 times a times c over 2. Now that 4 minus 8 gives me -4, and the square root of 4 is 2, and the square root of the -1 part would be I. So this is -2 plus or minus 2i over 2, which is going to look a little nicer if I split that up to get me -1 plus or minus I. As I alluded to before, we really just need to find the eigenvector for one of your eigenvalues. So let's just choose -1 plus I. So my alpha is -1, my beta is 1. Okay, so we do it the same way. How we were finding our eigenvectors is we took our matrix times the eigenvector that we have to find out what it is, equals the eigenvalue times my eigenvector. If I multiply this out, the first row, I get x1 minus 5x2 equals, that should be the top number here, and I just distributed, right? -x1 plus ix1. I got a bunch of x1 terms, so I'm going to add the x1 over here, that's 2x1, subtract the ix1, add the 5x2 term over to the other side. Note on the left side, you can factor out an x1, gives you 2 minus I. And if I divide that over, x1 is equal to 5 divided by 2 minus I times x2. One thing with imaginary numbers, we usually don't want to have them in the denominator. There is a way to get that out of the denominator. Remember, this is the square root of -1. So the old trick of the conjugate, if I multiply top and bottom by 2 plus I, the way that works is in the denominator, 2 minus I times 2 plus I gives me 4 minus I squared. Remember, I squared is really -1, so you're doing 4 minus -1, which is really 4 plus 1, gives me 5, which cancels out the numerator. So my well, no, that's not my eigenvalue. This reduces to 2 plus I. This part right here reduces to 2 plus I. So we're going to now find our eigenvector. Because now we know x1 is equal to 2 plus I x2. So this time it would make sense to choose 1 for x2, in which case x1 will be 2 plus I. There's my eigenvector. Now here's what I meant about the v and the w. We're going to take that eigenvector and break it up into its real parts and its imaginary parts. So if you think about 2 plus I, 1 plus, there's no I there, right? So the real part would be the 2 and the 1. And the I part, the imaginary part, well, there's a 1 there, and then there is no imaginary part for the bottom number, okay? So this vector here, the real part is what we're calling V, and the vector associated with the imaginary part we're calling W. And if you plug that into the solution, go back to the other page, your solution's going to look like this. That was vector V, that's vector W. Remember, beta was 1, so that's why there's no coefficient of your t's on your signs. Okay, as you can see, it's a bit of work.